Good day to you. Welcome. Thank you for coming along to the Thermo-fluid Gen Design Optimization webinar. We're focusing on space applications today. I'm Andy Fine. I'm going to be your host. I'm the CEO of the Fine Physics Technology Consortium, based here in the Colorado School of Mines out in the US. Joining me today, and I will introduce him shortly, is Dr. Peter Cullen from ToffeeX, and Jack Tuft, who is a propulsion engineer and expert on one of the applications we're going to be talking about. So if we kick off with today's menu, as I'm calling it, I'm going to give a little bit of an introduction into fine physics, what the Technology Consortium is, so the current software landscape. I'm sure all of you know that it's moving at a lightning pace at the moment. So I'm going to explain really where we are in the landscape. Then there will be an introduction for ToffeeX from Peter with some sample use cases and a deep dive into, I think, a very special application for rocket nozzles. If we have time at the end of the session, we will open up the floor for Q&A. So today's speakers, they'll introduce themselves briefly at the start of when they're talking, but Dr. Peter Cullen, who has his PhD from Oxford University on hypersonic re-entry. We have Jack Tuft, who's currently studying for his PhD at University of Glasgow, is a propulsion engineer at Orbex and has done work with the UK Space Agency. And I'm Andy Fine. I have an aeroacoustics background from Cranfield in the UK, and I've spent about the past 20 years or so in the engineering software industry. So the Technology Consortium, those of you who spend too much time on LinkedIn, such as I do, may well have seen this map. Now, this is a non-exhaustive list of just some of the startups and some of the engineering companies within the field of engineering in terms of physics or AI simulation. There's just way too many to actually look at, to be able to study at and integrate. So that's what we do at the consortium. We curate a technology stack that's complementary, that works together. And there's three qualifiers, which I'll be very clear about. A, has to be 100 times faster than any incumbent technology, has to perform a function simply not possible anywhere else, hence this is where ToffeeX fits in, and it has to be complementary to the rest of the consortium stack. So three very simple qualifying criteria for the consortium, and we at Fine Physics, we actually help curate some of this stack and cut out some of the noise within this. So product development optimization. This is something that we've been looking at. I think I personally have been working at for nearly 20 years. And I'm just going to guide you through this chart that you're seeing in front of you. So at the very bottom left, where we have an inefficient technique, small geometric design space, we've got the make it and break it. This is what we've been doing since prehistoric times. Now, over the past 20, 30 years or so, we've done more and more work on direct physics modeling. So here you can have, for a single design space, you can have a pretty efficient way of doing analysis using either CFD, FEA, electromagnetics, whatever it may be. I'd say 10, 15 years ago, we were doing parametric optimization. So we were limited to maybe 4 or 5 parameters. You could optimize the system for a set of targets. Things have come on a long way since then. So we've been able to do reduced order models for quite a long time with multiple parameters, but that's still you need a lot of expertise for that. You can have a mid-design space, and the technique efficiency is okay. Now, most recently, the last five or so years, there have been the AI surrogate optimization. This is the deep learning side. Now, there you can explore a big geometric design space, but the efficiency of the technique is pretty poor, if I'm honest. You need a lot of training data and a lot of effort going into that. And this is where we come at the very top here, which is the direct physics-driven gen design. Or the topology optimization, which we're going to go into here. Here you can have a large geometric design space, so many changes. You don't need to parameterize the system, and you can go through a significant amount of design iterations in a very short space of time. Hence, this is the area we're going to talk about here. So just to look at a little bit of a breakdown in that, a little bit of a timeline here. So we had from making it, breaking it, to the empirical formulations, where we had Newton, Einstein, and so on. And it was really in the 1980s that we had the direct physics modeling. This is when the codes were coming out of NASA and other bodies where you could actually do mathematical modeling, and there was enough computational power to actually do this. We led to parametric optimization at the end of the 90s and early 2000s, and that's the way a lot of things stayed. Whilst we boosted computational power, could do a few more parameters and so on. And then 2020s, we had this AI boom and AI surrogates and so on, but we're coming kind of over the curve in that one. So there's the hype of AI can do everything, and then the realization that you need to feed AI with a lot of data. And now, over the last few years, physics-driven gen design is really the way forward from this. It's been done in the structural world for quite a long time, and PhysicsX is bringing the CFD and thermal world into this. That's enough from me in the introduction. I'm going to hand over to Peter now, who's going to go through the details of ToffeeX.
Thanks a lot, Andy. Hi, everyone. Pete at ToffeeX here. So I'm part of the applications engineering team at ToffeeX. And what we do is we look at using this advanced topology optimization software to solve applied engineering problems. So who are we? We're a cloud-native generative design software. We're a spin out from Imperial College London, so based on the PhD research of our CEO, Marco. And essentially what we do is develop a software that allows you to have topology optimized thermofluidic designs for anything based on heat transfer and fluid flow, basically, so manifolds, cold plates, etc. Why is this advantageous? Well, it allows you to have optimal designs very quickly. It lets you explore the design space a lot more rapidly and fully because you can test out different design solutions more quickly. And it ultimately lets you have more sustainable designs because they become more efficient. These are some of the people we work with. It's on our website as well. I won't spend too much time on it, but what you can basically see is a real spread of industries. So from electronic schooling to aerospace, even some nuclear stuff, it's all kind of there. So please check that out afterwards if you're interested. Okay, so I want to talk a little bit about how ToffeeX works and where we fit in the sort of landscape that Andy mentioned. So this is how we see the world, in that there's the sort of overarching computational design, which you can really think of as anything that uses computational methods to achieve a design. Maybe then within that, as a subset, is generative design, where either AI or algorithms can produce designs autonomously. So this takes the human out of the loop to an extent. And finally, we have topology optimization, which is a specific subset of this. So we have a mathematically based design approach, which gives you the most efficient material layout for a given set of constraints and objectives. And so this is where we sit. I find this can be a little bit abstract. So let's maybe talk about how this works. So you define a design domain and some physics and design parameters. So you can think of this being very similar to a CFD setup. Here we have a rectangular channel. We have an inlet and an outlet, a couple of heated walls, and then some symmetry planes. You discretize the domain, and it's a function of the solidity in the domain. And then what we do is go through this iterative approach where we solve the CFD, build material based on that result, and then update the design. And if we've not converged, we go around the loop. And if we have, we finish the design. So what does that look like in practice? Well, this is a sped up animation of what the design process looks like. So through the course of the optimization, the solidity is starting to find the optimal design, and it eventually converges out to a final geometry. I say this is sped up. This probably took 15 minutes in real time, in computational time on our cloud, but here it's a couple of seconds. The advantage of this approach is it's CFD coupled to the design. So at every point you're solving real physics, getting a real picture of what's happening, rather than relying on interpolated models or training data. Just a little bit about where we sit. So we see ourselves as sitting somewhere between a design and a proper full analysis tool. So the idea is that in traditional design iterations, you might manually design something, you put it into a CFD code like ANSYS or CCM, see how it performs, and then you might manually adapt the design and go around that cycle iteratively a few times. The purpose of ToffeeX is to break that iteration cycle, and so reduce the number of times you need to go around that iteration loop, meaning you get to the best design more quickly, which ultimately saves you engineering time and speeds up your product getting to market. Okay, so that's a very quick background about who we are and how we work. please see our website, and we have some other webinars and white papers if you're interested in the sort of the fundamentals of the technology. But what I want to focus on today is maybe some applications that are of interest to the space industry. We do a lot of things, which is kind of what this slide is showing. On the left is applications that are maybe more thermally based, and on the right, maybe more pure fluid applications. And today, I'm just going to very briefly touch on cold plates for a sort of a thermal side, and then manifolds as well. So, quick example of a cold plate. This was something that was done recently with one of our partners, Rico. Flow inlet comes from the side, outlet on the other side. They essentially had a pin-fin heatsink that they made of copper. That was the baseline design. And what they wanted to do was to replace that with an aluminium design that they made through a 3D printing technique called binder jetting technology. So in ToffeeX, we define our design space. We built kind of 3 main design spaces or sections above some heated chips. And the goal was to minimize the pressure drop and the temperature whilst reducing the weight. So based on your preference between how much pressure drop you're willing to trade off against temperature, that gives you sort of a Pareto front of designs. And that's what this is showing here, 3 example designs where in this one, we're favoring pressure losses more than heat transfer. In the bottom one, heat transfer more than pressure loss. And then the middle is kind of a balanced design. So we maybe take this balanced design forward. It was manufactured using the technology, and they managed to actually experimentally test these. So what you see here is that the copper design has this amount of thermal resistance, but it's obviously quite heavy, being about 3 times as dense as aluminium. If you were to make the same pin-fin design out of aluminium, you see that the weight drops quite a lot, but the thermal resistance goes up because it's less effective. Finally, with the ToffeeX design, the weight is about the same, swapping the previous design to aluminium, but we get actually a reduction in thermal resistance. So a huge weight decrease and actually an performance increase as well. So a very good result. You can see it on test up here. Okay, very brief examples of some manifolds. So this is sort of a die cast manifold we've worked on previously. The incumbent design, you can see here, it's 4 inlet pipes leading to 1 outlet. The main issue was this pretty significant velocity non-uniformity on the outlet face. So again, using ToffeeX, in this case, optimizing for improved velocity uniformity and reducing pressure drop, we arrive at this design on the right, which is about 60% lower pressure drop and much more uniform velocity on the outlet face. So a good result. This second application for the manifolds it's actually the subject of a previous webinar, but I really like it for the reason that what we're doing here is optimizing the header of a shell and tube heat exchanger. What happened previously was the flow would come in through the top. It obviously gets just straight through these middle tubes. The outer ones were being ignored or not receiving as much flow. With a ToffeeX design that was additively manufacturable, it achieved much more uniform velocity. And what it actually did was, just by improving the velocity distribution, improves the heat transfer in the core by about 15%. In some applications, potentially where you have a really advanced heat exchanger you've worked on for ages, you can use ToffeeX to just eke out that last bit of performance that you really need to make your design. So yeah, just an extra interesting use case, I think, for the manifold design there. Right. The focus of this talk is the rocket nozzle work we've done. So I'd like to maybe briefly introduce Jack Tuft. He's a guest speaker. He was working on this project as part of his PhD at the University of Glasgow. Jack, maybe you could just say a little bit about yourself and about the project, and maybe tell us what regenerative cooling is.
Yeah, cheers for a short introduction. So yeah, my name's Jack. I'm focusing on regenerative cooling optimization in my PhD back at Glasgow, and rather than focus on parametric optimization, I really wanted to do something a little bit more left field, look at generative design and different methodologies. But now I've paused my PhD for a short break to work in industry, so I'm working at a company called Orbex. Orbex a launch service provider based in the UK, and I'm based in Copenhagen because that's where all the propulsion activities are. But for anyone that doesn't know, regenerative cooling is essentially where we use the propellant of the launcher to cool the rocket engine, and it's the most commonly used cooling methodology in propulsion systems. Yeah, you've got combustion temperatures of about 3000 Kelvin, huge convective heat transfer. So what you're doing is you're passing that propellant down to the bottom of the nozzle and then back up towards your injector. So dually beneficial, so you're not only just keeping everything within a thermomechanical limit, you're also keeping that energy within the system and absorbing that within the propellant. So yeah, without getting into it too much, I hope that kind of covers it, Pete.
Yeah, that's really interesting. I'm just wondering, just as a question, is it always counterflow to the nozzle? So I guess here we have the exhaust flow coming out and the coolant flow going from the outlet of the nozzle up to the combustor. Is that always how it is?
Yes, because you are injecting that. So you can do dual pass, which would be kind of, you can see it on that one, on that top image there. So you go down the nozzle first and then back up, but it always ends up by the injector because that's where your propellant comes back up and then is injected down.
Fuel goes in the fuel injectors.
It
That
does
makes
indeed,
sense.
yeah.
Nice. Okay. So I'm just going to briefly talk about how we'd set this problem up in Toffee, and we took two approaches. The first is a 3D design approach, so taking a segment of the nozzle. An advantage of ToffeeX is that you can constrain regions to be either not built in, to be built in as part of the design process, or to be completely solid. And if you model stuff as completely solid, then you account for the conduction as well. So in this case, this is a section of the nozzle. In red is the solid wall constraint. So the wall, basically that's the inner casing of the nozzle. Jack, roughly what thickness is the wall of the nozzle?
1 mil.
Okay, yeah, so it's about 1 millimeter thick, so it's quite a thin domain. On the right-hand side, so I know flow goes left to right, we all know this, but the nozzle flow in this diameter in this diagram is left to right, and then the coolant flow is right to left. So the flow comes in from the right to cool it. We have an inlet and an outlet for computational stability, which we don't build in, and then we have the design domain up here. As Jack mentioned, the heat fluxes can be really high. They grow up towards the throat. Do you know roughly sort of what the orders of magnitude of these heat fluxes are, Jack?
Yeah, so not quite the same as that graph. We're talking about at least an order of magnitude higher at the throat. So as you're going from left to right with the flow of your combustion gases, as that reaches the sonic condition at the throat, that's where your heat flux spikes.
And do you ever get nozzle ablation? Is that a problem in the
Yeah,
rocket
it's
nozzles?
very, very common. Yeah,
Okay.
that's why you've got to be really on the ball with your cooling.
Okay, makes sense. And maybe just for context, I mean, what do existing designs look like to solve this kind of cooling problem?
So typically you've got just straight channels going from the base of your nozzle to the injector, but you also see helical channels that spiral up around the nozzle as well. Basically,
Okay.
essentially what you're doing there is increasing you've got more heat pickup, so you've not got as effective cooling because your propellant is heating up, but you have a longer path per axial distance.
Okay, interesting. And I mean, are there any sort of well-known issues with those designs that made you want to look at topology optimization?
Yeah, so you're always trying to balance out that pressure drop, and you've got printing constraints about how thin your channels can be and what orientation. If you're just going to do straight channels, then you are limited by your actual nozzle geometry. So I wanted to look into how we can kind of locally solve this heat flux issue. Since we've got an order of magnitude higher heat flux at the throat, can we use generative design to our advantage and locally cool places more than others?
Yeah, nice, makes sense. So I have a little example of the output from ToffeeX here. So again, an animation of the development of the design across the design iterations. What you can see on this picture on the right is just the development of some interesting flow features for cooling. So there's a bit of thickening of fins at the throat, and then a development of some interesting cooling features at the hotter end. So you can see here some fins with actual cooling holes through them. So basically micropore holes that allow the flow to. I actually do have a question, which is normally, I suppose, if you traditionally see rocket engines, they tend to be bigger at the outlet than the inlet. I'm just wondering what the purpose of that is for the design. Is it because it's at sea level?
Yes, so it's partially because it's at sea level, also because our chamber pressure is very low. With your expansion, you are essentially taking your combustion chamber pressure and then you're expanding it to whatever condition you want. I wanted to essentially make these engines as robust as possible, so really low chamber pressure. But since this is a test bed engine, it has left us with a nozzle contour that doesn't look very rockety, is probably the best way to put it.
I mean, I feel like if it fires propellant out at the end, it looks pretty rockety,
It does indeed.
But I suppose a feature of that is even though the heat flux is highest at the throat, the water is very cool because the outlet isn't that long. So we might expect with a bigger nozzle, you'd have a lot more construction of fins at that point.
Exactly.
So I think, is that fair?
Exactly.
Nice.
Yeah, exactly. I think one thing that we were kind of surprised to see when we were doing this, Pete, is that we saw a lot of these features go towards the end of the like the injector side on the left-hand side. And that's actually just because our propellant, these are water-cooled engines, was heating up so much. Where the fluid actually needed to do the work was by the injector rather than at the throat. So that was quite interesting.
Yeah, I suppose it slows down quite a lot as well coming in. Like, you know, it has to expand out, the velocity drops. Yeah. But no, it was kind of good to see that it follows, you know, the physics of that happening. You can kind of get a sense of why these designs are being created and the physical reasoning behind it. Okay, so the other thing we tried was a 2D approach. So the previous design I just showed, that probably took about 10 hours on 16 cloud-based CPUs, which is slightly less than our customers would normally have. This one is maybe more on the order of an hour to do in 2D, so it allows a bit quicker design iteration. So on this, we took this 3D design slice, mapped it to an equivalent flow area. So obviously, as you're going out radially, the area increases. So accounting for that in this equivalent area, 2D design, then using ToffeeX, come to a 2D solution. And then we remap that and rotate it back to the 3D nozzle and validate it, obviously, then in 3D to check that the design still works. I suppose maybe a question I should have asked you sooner, Jack, is like, considering this and the 3D optimization, are there other tools you thought about using for topology optimization? What do you think the blockers are to those being used maybe successfully in industry? Did you find that ToffeeX was particularly useful for this case?
Yeah, so just before we started working together, I also did topology optimization of just a example microchannel kind of heat sink with that variable heat flux to mimic a rocket engine, just to do like a very first case. And I used ComSol multiphysics for that application, but I did a short intensive course on topology optimization, and then only after months and months of trying to get this model to work and academics who already had other models and helping me along with that I actually managed to get those results. It's structural topology optimization, I think, is certainly a lot simpler, but as soon as you move into that fluid domain, it's just exponentially more difficult.
Yeah, I mean, and I guess that was like text files, terminals.
Yeah, ComSol multiphysics is it is still quite user friendly. Like there are modules built in for it, but it's I think the focus of that, certainly from the last time I've used it, was more of a structural application. It does work. Like I still managed to get it to work for the fluid stuff, but it was difficult.
Yeah, that makes sense. Okay, so here's an example. These are some example designs we got to, or the final designs we got to. What you can see is this is the simulated conventional design, as Jack mentioned, with straight cooling channels. It gets very hot at the outlet based on that expansion of the flow, and so reaching a max temp of about 440 Kelvin. You can see that the 2D design has about the same pressure loss, but is much cooler. And the 3D design that we arrived at was slightly higher in the pressure losses, but then much colder as well. So depending on the design requirements and how you want to trade off those results, designers can make decisions about where they want to be on that Pareto front, what design they want to take forwards. But overall, I think a good result, good performance found with ToffeeX, and some promising reductions in temperature. So that was kind of the computational side. I want to talk a little bit about the outcomes in sort of real terms, and then maybe we can move on to the Q&A. So these are two test pieces that we had printed for display, or it's actually one test piece from two different angles. We had some friends at 3DNA in Italy print them for us, but this is a single nozzle with the 3 different cooling types on the side. Jack, I can't remember, was this scaled down or is that full scale?
I think it was to scale. Yeah, I think so.
Yeah. Okay, yeah, so a full scale nozzle.
Good question, actually. Not sure.
Yeah, I mean, it's just the display one, so I guess it's less critical. But you can see here the conventional design with straight channels, the 2D remap design with sort of branching cooling passages, and then finally this advanced 3D design with the sort of aerated fins that appear at the end. These are the final test pieces. Jack, do you maybe just want to say a bit about how the testing works, what the setup is, where you're doing it, that kind of stuff?
Sure thing. So we had three chambers printed, all for the straight channel, 2D and 3D topology optimized results. So torque, topology optimized regenerative cooling, 1, 2, and 3. And these were printed out of a material that's quite common in rocket engines called copper chromium zirconium. So it's kind of high strength, high thermal conductivity material. And these are all water cooled. So we kind of wanted this to be a first step in the TRL increase of doing this kind of thing. We didn't want to just jump straight to using propellant. With the water cooling, we can adjust that on the fly if we're seeing thermals that we don't expect. But these are all tested at MacLab. So it's a University of Glasgow project that's been going on for a couple of years now, and the site's now fully commissioned. Unfortunately, there's no hot fire videos, where that's all getting released in the next couple of weeks as a big data package, a big media package. But it's a cryogenic, so liquid oxygen and kerosene facility based in Scotland.
Nice. And just for clarity, I mean, so we obviously don't see the internal structure as we did on the display pieces because it's got a casing, which makes sense. We don't want the coolant flying out. What are these sort of ribbed lumps with the holes?
Yep. Yes. So they're thermocouple ports. So they're not wetted thermocouples. They're dry. But on each of the, it's quite hard to see, but underneath torque 2 there, you can see that water cooling outlet manifold. Yep. And then the one directly above that, that's the water cooling inlet. And so there are wet thermocouples. So then we can correct for that temperature distribution across the axial length of the nozzle. We've also got 2 pressure sensors in each of the manifolds as well. Yeah, I think that's all of it.
Nice, thank you. Okay, so this is an example nozzle on test. I mean, this, you said this was this at that facility?
This is at MacLab, yeah. So that was South African research partners that came up to the site just before my tests.
Great, nice. But so you said there's no hot fire videos at the moment. I think when they're available and the press is released, if you follow us on our socials, we'll release the video as well. But you can tell us that we've tested the 2D design and it survived.
Yeah, so the 2D one performed very well. So it was a 25-second long duration burn, but there was a number of different tests done. Time was a bit tight, so they didn't manage to test the 3D one, but that'll be coming in the coming months as well.
Amazing. But yeah, I guess maybe as a summary, you know, we've used ToffeeX to develop 2 advanced designs for these regenerative rockets in a 2D and a 3D sense. Both of them have reduced the temperature of the nozzle wall significantly, and they've been manufacturable and testable, which I think is a really key outcome. You know, you can have some of these pictures be really pretty, but actually having something that you can build, test, and doesn't blow up is quite a nice outcome, I think. Sorry, what's the rocketry term?
Rapid unscheduled disassembly.
Yes. Okay. Thank you. Sorry, that's
No
the lack of the limit of my technical knowledge. Maybe just one more, and then we could go on to the Q&A. What do you see other uses for TO in rocketry?
Yeah, absolutely. So there's a number of things that I would love to explore if I had the time. So volute design. Within rocket engines, the most complex part is the turbo machinery, and so you've got volutes there for the actual regenerative cooling inlets. Very, very important, and a lot of work gets done to ensure that you have an even velocity profile and even mass flow distribution around those regenerative cooling channels. Otherwise, you'll end up with hot spots, potentially burn through and cause a rud, as you say. Injectors as well. So with your propellant coming in, about how you actually achieve a uniform flow distribution. And then there's obviously the cooling aspect of it as well. So you've got regenerative cooling, but one thing that you're seeing a lot more on is electric pumps. So there's companies that use electric pumps more and more. Well, Rocket Lab, their Rutherford engine is fully electric, and all of those electronics need to be cooled as well. And they're actually cooled with your rocket's propellant. So, you've essentially, a rocket is just one big fluid network, and you're really trying to optimize for that pressure loss and just optimize. If you can reduce your pressure drop, then upstream you get benefits and mass savings and all the rest. So yeah, lots of different applications there.
Okay, interesting. So for example, the cold plate example I showed at the top of this webinar, you have electronics very similar to that in a rocket engine, which you'd also be cooling with the fuel.
Yeah, definitely. So there's a lot of electronics that aren't cooled, but as soon as you bring, like high power requirement pumps into it, they need cooled actively rather than passively.
Yeah, that makes sense. And I mean, the volutes, I suppose, are basically manifolds, and there's fuel manifolds everywhere. So I think that's
exactly. Yeah.
Nice, great. Cool. Well, I think that's all we had directly to present, but we probably have a little bit of time for Q&A. Is that right, Andy?
We've got about 3 minutes left. So if there's
Nice.
a couple of questions we can address them, more than happy to do that.
Okay.
I think just just before we go to the questions, I just want to personally thank you, Peter, and thank you, Jack, very much for taking part in the webinar. If you have further questions, you'd like to find out more about ToffeeX, or you want to know a little bit more how the application can work for you, your US contact is afine@finephysics.com. Within EMEA, Charlie will be happy to help you on c.kelly@toffeex.com. With that, I think we've got time for 1 or 2 questions.
And just for clarity, there's a Q&A section on the chat if you're interested in asking anything. Okay, so the first question is, does this model consider phase change? So currently, if we're talking about phase change, currently we don't consider phase change. What I would say is that the Paris Air Show recently, it was announced we're part of this larger project with Airbus called DECTAM in the UK, so basically advanced design for additive manufacture. And I think one of our things we are interested in looking at in that is phase change. Coming from an aerothermodynamics background, the heating and the flow in the nozzle can be quite non-equilibrium, especially if you have fuel. You can have wall casuality, that kind of stuff. You can use the output of another CFD code directly as a non-uniform temperature boundary condition into ToffeeX. So if you have really advanced, say, physics in the main bulk of the flow, you can account for that wall heat flux in the optimization, so you don't need to model it directly. So that's one way that we can still work in these sort of really challenging multi-physics environments. That might be it for the questions, unless anyone has any more.
No. Okay.
Now, hold
Well,
on.
there's one more question.
One more has come through. You're able to evaluate. So the question is, when you do the TO, are you able to evaluate the structural integrity with stress loads as well, or are you limited to thermal transfer, velocity, and pressure drop? Currently, we would solve that in an uncoupled way. So it's something you'd look at afterwards. And we can use stuff like minimum feature size to make sure that, say, for pressure loads, the wall thickness is always above a certain amount. But we would expect, I think by the end of the year, we'll have a level of structural analysis capability within ToffeeX as well. So I think the answer to that is coming soon.
Okay. With that, I'm going to close out the webinar now. So thank you once again, Jack. Thank you, Peter. Please do get in touch if you've got any questions. With that, I wish you a very good day.
Thanks, Andy.
Thanks. Cheers.
Cheers.